Where do birds come from? And who were their ancestors? For a long time, these questions have remained unanswered. Their family tree stopped abruptly at the oldest known species, a fossil found in 19th century Germany, Archaeopteryx, whose name comes from the Greek for ancient wing. But since 1996, thousands of animals unearthed in China have shed new light on the origin of birds. This abundance of discoveries proves that most dinosaurs were not covered in scales, but clad in feathers. Some of these feathered dragons could even fly. The extent of the Asian jigsaw puzzle is so vast that it ties modern-day birds to remarkable distant cousins and suggests a multitude of relatives. During the Jurassic period, between 200 and 145 million years ago, the supercontinent Pangea opened up, creating separate landmasses. At the edges of this world, China and Siberia formed a huge peninsula with a temperate climate similar to that of modern Europe. The breakup of the continents was accompanied by volcanic eruptions, particularly in China, a paradise in waiting, inhabited by strange creatures like Anchiornis. Meaning near bird. This little dinosaur is completely covered in feathers. The size of a modern-day pigeon, Anchiornis is a long-lost relation. The descendants of this lightweight dinosaur survived better than other large theropods, a group that includes all carnivorous dinosaurs. Including guanlongs. They are efficient hunters, 3 meters long and weighing 50 kilograms. To escape, Anchiornis was capable of short gliding flights, while its pursuer was firmly stuck on the ground. And yet, guanlongs also had feathers. What were they used for? Erupting volcanoes spewing fine ash and noxious gases froze a moment of Jurassic life for eternity, helping us answer some of these questions. This dinosaur paradise has become the feathered dinosaurs' Pompeii, A huge range of new species has recently been discovered in one of China's many construction sites. Over the last 2 decades, in the Liaoning region, paleontologists have collected thousands of specimens, hidden for millions of years. These magnificent fossils are in a state of almost perfect preservation, thanks to the mixture of extremely fine clay and volcanic ash sediment.
And those volcanic eruptions killed the animal directly and they buried their body. So that's why we have so beautiful skeleton and include soft tissue preserved. So that's why we come here.
Paleontologist Xu Xing and his colleagues from around the world can trace the chaotic history of flight and feathers in these rocks.
The feather preservation is really amazing.
Like detectives, they examine the clues to understand what feathers were used for. And discover how some dinosaurs from the theropod family turned, over the course of millions of years, into birds. The first piece of evidence in their inquiry was discovered at the end of the 19th century in Germany. Towards the end of the Jurassic period, Europe was partly submerged under a shallow body of water called the Tethys Sea. About 150 million years ago, Germany was dotted with tropical islands. Pterosaurs, the first flying vertebrates, have dominated the skies for 80 million years. This is Germanodactylus, one of 150 species of pterosaurs discovered. These flying reptiles are not dinosaurs. A fine skin stretches over their elongated fingers to create leathery wings. This membrane, along with powerful muscles and hollow bones, makes them masters of the skies. But the pterosaur's aerial supremacy is about to be challenged by the very first birds, such as Archaeopteryx. A primitive bird whose claws at the ends of its wings raised suspicions amongst 19th century paleontologists. Its fossils were found around the modern German town of Solnhofen, a tropical archipelago during the late Jurassic period. Some islands harbored salty lagoons where dying animals avoided scavengers, and were buried by soft mud that preserved them in minute detail. Eberhard Frey, commonly known as Dino Frey, is the resident expert.
This is the famous Solnhofen laminated limestone, and you can actually see the sediment stapled up like the leaves of a book. And inside the leaves of this rocky book, this is where Archaeopteryx was found together with many other fossils. And it's a speciality of this rock that it is very, very, very fine-grained. And inside this mud, fossils are preserved like in a tin. And this is why this entire area is so valuable as a window in Jurassic times.
The locals use these stones to tile their houses, in the process uncovering highly prized treasures in the history of paleontology. In 1868, faced with the Archaeopteryx, British biologist Thomas Henry Huxley asserted that this was a transitional fossil between reptiles and birds. A friend of Darwin and an ardent defender of the theory of evolution, Huxley was an expert anatomist, capable of skilled fossil analysis.
And until the year 1861, before Archaeopteryx was discovered, the only creatures that were known to have feathers were the birds. So it was apparent that this is a fossil bird. And Thomas Huxley looked at it very closely, and he discovered signs that this bird could also be a dinosaur, actually a carnivorous dinosaur, and actually shares characters of the two, making it a missing link between dinosaurs and birds. That was a sensation at the time.
The Darwinian idea of natural selection is therefore very recent. Huxley had the insight to see that Archaeopteryx's teeth, clawed wings and bony tail meant that it had similarities with compsognathous dinosaurs, predatory relations of the velociraptors. Archaeopteryx was certainly no acrobat, but it had feathers, and it could fly. Its collarbones had already fused together, a vital step enabling the wings to flap efficiently and gain altitude, allowing it to hunt and nest in trees. Throughout the 20th and 21st centuries, more Archaeopteryx fossils were unearthed in Germany.
This is specimen number 11. It's the latest specimen, and it came to light in the year 2011. And despite its fragmentary, it's not completely preserved because the skull is missing, it still shows us some features which were previously unknown. One of them is that the tail end shows a V-shaped feather configuration. And the second is that you can see in this specimen the extent of the feather troughs along the legs.
The feathers on its feet are intriguing, since modern birds no longer show this characteristic. Is this an exception? What is sure is that this feature has not been selected by evolution. Just like this giant marine reptile, a Leopleurodon. Washed up on the shores of the lagoon, it is a godsend for Archaeopteryx. The flies attracted by the carcass provide a hearty meal for this insect eater. But being out in the open is dangerous for Archaeopteryx. An opportunistic Germanodactylus sees the prospect of a protein-rich meal. And doesn't appreciate the competition. Once the mightiest creatures in the skies, pterosaurs became extinct by the end of the Cretaceous period, 65 million years ago, while Archaeopteryx's descendants grew in number. Bogged down at the bottom of the Solnhofen Lagoon, this remarkable fossil launched the debate on the relationship between birds and dinosaurs. But with insufficient proof, this theory was shelved for more than 100 years. Until new evidence came to light at the end of the 20th century in China. In 1993, in Liaoning, a huge fossil deposit was found dating from the Cretaceous period, 125 million years ago. This region, formerly known as Manchuria, comprises fertile farmland with fields of corn and pasture. Farmers were the first to uncover fossils inadvertently in Sihetun, at the foot of a cliff fashioned by volcanic eruptions. Layers of grey mud alternate with red ash. Transported to Beijing, these fossils allow 21st century researchers new insights into the feathered dragons. Like Sinosauropteryx, the first discovered in 1996. This specimen remains a source of fascination for one of China's most famous paleontologists, Xu Xing.
I remember clearly at that time when this discovery was announced, everyone got so excited, we are kind of shocked by the beauty of the fossil. If you look at this specimen closely, you see the feathers cover the whole body, over the head, over the back, cover whole the tail, a little bit here also, limb. Basically, feathers are quite simple. They are more like your hair. Before this discovery, some paleontologists believe some bird-like dinosaurs should have feathers, but now we have real evidence, so that's totally different.
The discovery of this feather-covered fossil was astounding. For the first time, they had found a dinosaur with avian characteristics, proof that they were part of the same lineage. In conifer forests, growing in the shadow of volcanoes, lived Sinosauropteryx. It belonged to a group of carnivorous dinosaurs called theropods. These predators use sight and smell to hunt. One of its favorite victims is Zangiotherium, one of the first mammals. Sinosauropteryx feathers look like the down covering modern-day chicks. They are so different from bird feathers that for a long time, skeptics dismissed them as mere hairs. In 2010, Xu Xing focused on Sinosauropteryx's strange feathers, which look like the down covering modern-day chicks. He began with careful observation of these feathers. By taking a sample and putting it under the microscope, scientists discovered fossilized pigments. These are melanosomes, cells that give feathers their color. Xu Xing discovered circular shapes that produce a brown pigment and stick-like shapes that create a gray color. He deduced that Sinosauropteryx was the color of a squirrel, with lighter stripes on its tail, but that's not all.
We can use melanosome to infer the color, but more importantly for us, we want to use that information to support the hypothesis that those dark impressions in this particular specimen are protofeathers, not something else. Because if melanosomes are present, we can see quite confidently those are primitive feathers.
Sinosauropteryx was undoubtedly covered in feathers, but this land animal was incapable of flight. So what use was this dino fuzz? Did it protect this warm-blooded animal from the cold? Possibly. But this theory is not easy to prove. To learn more about the climate in Liaoning during this period, Xu Xing teamed up with a laboratory in France. This theropod tooth, brought back from China by geologist Romain Amiot, holds the key to this meteorological mystery.
A lot of researchers thought that fossils from that time couldn't preserve the weather conditions recorded during the animal's lifetime. It was a big challenge. We were going to test something unknown. Could we find out climate information or not?
In a sense, we can test the water that the dinosaurs drank. A chemical reaction with the oxygen preserved in tooth enamel reveals the temperature of the atmosphere 120 million years ago. Romain made a major discovery that radically altered our preconceptions.
At that time, there was a global climate that was similar or a little colder than current temperatures, which is very different from what we thought about the period of the dinosaurs that we had imagined as hot, tropical, and the same throughout the world. Where Liaoning is, the climate was similar to what we have in the north of France, with very harsh winters. So dinosaurs would have seen snow in winter. So feathers were an insulating material. It meant they could keep warm and keep active throughout the year, like any other warm-blooded animal.
Coincidentally, just as Romain published his research, the discovery of large-sized dinosaurs confirmed his work. Eutyrannus, the aptly named feathered tyrants, were the super predators of the time. Due to their large size, the remains of T-Rex's cousins are kept in a warehouse in a suburb of Beijing.
Eutyrannus is a really amazing animal. You know, it's a really big animal, about 1.5 tons in body mass. Its body covered by feathers, really long feathers. So this is unexpected. You know, traditionally we thought, you know, when animals get big, for dinosaurs, same, those feathers, reduced feathers, or at least feathers are kind of sparse. But here we have a large-bodied dinosaur with dense and long feathers. So this is bizarre.
The fact that such a large, warm-blooded animal was covered in feathers suggests that its body size was not sufficient to regulate its temperature. so the climate must have been very cold. The discovery of the largest feathered animal ever found confirms the hypothesis of a temperate climate with harsh winters. It proves that the theropod dinosaurs of Liaoning wandered into the winter snow 125 million years ago, and that the feathers of the little Sinosauropteryx and the huge Eutyrannus protected them from cold temperatures in this region of the northern hemisphere. The insulating property of feathers remains a feature in modern birds. But it is not sufficient to explain how surface-dwelling dinosaurs evolved over millions of years to become birds. Among the theropods living in Liaoning, was there only one type of feather? And at what stage did dinosaurs begin to fly? Over time, Chinese paleontologists have unearthed many feathered creatures. On some fossils, like the Caudipteryx discovered in 1998, Xu Xing found feathers that were not just simple filaments. With its large feet, it looks much like an ostrich.
In this fossil, there are some really beautiful feather impression. Here you see two hands of this animal, and here is the middle finger, and you see feathers attached to the finger, this surface, and they go this way, so it's quite a big feathers.
Caudipteryx, literally meaning tail feather, comes from the same Chinese site as Sinosauropteryx in the same period, 125 million years ago. Scientists imagine that these chicks were imprinted on their mothers, just like modern birds, and followed them everywhere, more or less. Weighing almost 20 kilograms, the female Caudipteryx can't fly. Neither can her youngsters. So why do these animals have long feathers? Could they serve a purpose other than warmth? Feathers begin as a simple filament, which divides to form a pom-pom before barbs appear around the hollow shaft. But at this stage in their development, feathers are symmetrical and air passes through them.
So it is not flying animal, it's fast-running animal living on the ground. So what's the function? Apparently those feathers are not used for flight. So the other possibility, most people believe, is display.
Just like many birds, the males and females were physically very different. Paleontologists believe that the male Caudipteryx displayed his shimmering feathers in order to attract females. These courtship rituals, along with natural selection, stimulated an anatomical transformation. Caudipteryx were among the first theropods to possess a shorter tail that supported their display feathers. In order to fly, they were still missing a fundamental element: flight feathers. Seen under a microscope, this feather comes from another dinosaur, discovered in 2000 by Xuxing himself. It is a vital clue to solving the mystery of the origin of flight.
Here, the feathers are highly asymmetrical. So asymmetrical feathers are normally considered to be associated with flight capability.
These feathers are identical to those of modern birds. It may be proof that some dinosaurs could fly.
Microraptor is definitely the most amazing species discovered so far. It is a dinosaur, but you see it has asymmetric flight feathers, not only the feathers on the arms, but also on the feet. So we call it four-winged condition. This is really, really bizarre. And now we have quite good evidence suggesting this four-winged condition is related to the origin of flight.
For a long time, paleontologists believed that two-legged dinosaurs ran along the ground in order to take off. But Microraptor's climbing claws opened up a new possibility. 125 million years ago, in the part of China that Microraptor called home, the ground was fertilized by volcanic ash that encouraged the growth of lush vegetation. Tall trees add a vertical dimension to the landscape, and the Microraptor, meaning small thief, takes advantage of them. Microraptor sported feathers on its arms and legs. With its four wings, it was probably the world's first base jumper. Four wings offer an advantage for gliding, but not for walking. A Microraptor on the ground is a Microraptor in danger. According to Xuxing, tree-dwelling feathered dinosaurs like these would evolve to become birds. To better understand this transition, paleontologists teamed up with an ornithologist, Zhuzhongyi. In front of him is an incredible collection of primitive birds found at Cited. Like the feathered dinosaurs from the same site, they all date from the Cretaceous period, 125 million years ago.
I think there are over 500 specimens of Confuciusornis are collected in this museum alone. I think this is the largest collection of Confuciusornis in the whole world. This bird, like Confuciusornis, they are only shortly later than the earliest bird, Archaeopteryx, and they are transitioned in many flight apparatus, many features.
Despite the claws on their wings, they are very similar to modern birds. They no longer have teeth or a long bony tail. They also have a furcula, the famous chicken wishbone, for attaching muscles to wings. And the males have two ceremonial ribbons ornamenting their behinds. This sexual variation is similar to that of the feathered dinosaur, Caudipteryx. Like him, the male has long feathers that he uses to lure the ladies. Competition is tough, and courting displays are often interrupted.
Also, you can see the bird start climbing the trunk with very big claws in the wing. Now you see the bird can perch on the branches of the trees because the helix of the foot is already reversed, much like a modern bird.
Confucius ornis's narrow feathers were not well adapted to gliding, but would have allowed it to fly by flapping its wings, albeit clumsily. But natural selection is at work, retaining only the most adept genes. Yet the presence of many birds found at the same location as feathered dinosaurs does not necessarily prove that they were related. If birds had already diversified 125 million years ago, Eutyrannus and other theropods may have been merely an evolutionary dead end. So when did the first birds appear? Did they share a common ancestor with feathered dinosaurs? And how did their ancestors begin flying? To answer these questions, Chinese paleontologists have one last card up their sleeves. West of Liaoning, a new fossil bed was revealed during the construction of a motorway. In 2009, a finely preserved Anchionis, dating from the Jurassic period, was found near here. Was to become a crucial piece in Shuxing's puzzle.
This site is very important for, at least for one reason. We know that Archaeopteryx, the earliest known bird, is from about 145 million years ago. But most other feathery dinosaurs are, from early Cretaceous or even later. So this dinosaur was living in like 160 million years ago, earlier than Archaeopteryx. So that means there are some feathery dinosaur predates Archaeopteryx, the earliest bird. So that's correct time sequence.
This new fossil puts an end to the debate. Feathered dinosaurs are undoubtedly older than the first birds. Today, Shuxing discovers a fish, confirmation that Anchionis lived in a rich ecosystem. This little four-winged theropod must have been a victim to giant predators. In the Jurassic period, pterosaurs, like these Darwinopterus, ruled the skies. With talon-like claws and a wingspan over a meter wide, they were the equivalent of modern-day birds of prey. Their ability to fly and perform aerial acrobatics was beyond that of the feathered dinosaurs. Faced with this constant danger, Anchiornis sought shelter in the forest. But this little dinosaur was also threatened from the ground. Its only shelter lies in the restricted area between the ground and the sky, the trees. It glides down to feed in the undergrowth. Its surface area is smaller than Microraptor, so it falls more quickly. With its long back legs, Anchiornis is built like a sprinter, but its lengthy feathers are a hindrance on the ground. Its long legs are an advantage for foraging or rushing to the nearest shelter, if such a thing exists. Clumsy, Anchiornis showed that dinosaurs attempted to fly from trees using 4 wings. On this rare fossil, the rear leg feathers are visible to the naked eye. To refine his theory, Shuxing continues his research using a medical scanner. X-rays of Anchiornis' skeleton will be digitized in 3D in order to study its biomechanics.
But honestly, there are some debates how exactly those animals use their leg wings. Some people believe the leg wings are not really related to flight. Maybe it's a display structure. If we look at other dinosaurs, their leg normally is underneath the body. They have sort of like fully erect posture. One possibility may be Anchiornis can project its leg slightly laterally.
To compensate for the lack of a wishbone, Anchiornis used its rear leg feathers to improve its gliding ability. The discovery of Anchiornis proves that dinosaur flight was a result of trial and error in the evolution of anatomy and feathers. Surprisingly, new information about the origin of feathers was soon to appear from over the border. In Siberia, in the summer of 2013, the first Russian feathered fossils made their appearance. "1,500 kilometers north of Beijing, in the Trans-Baikal steppe, a team of Russians and Belgians worked together at the excavation site. When local geologists found the first bones, they invited paleontologist Pascal Godefroy from the Royal Institute of Belgium to take part in this revolutionary discovery.
We're at the Kulinda deposit in southeast Siberia. The hills you can see behind me date from the Jurassic period between 145 and 160 million years ago. And Russian geologists who were prospecting in the area in 2010 found the first dinosaur bones, which have been extremely important for reconstructing the evolution of plumage and feathers in dinosaurs.
His curiosity aroused, Pascal assembled a team to search the site for themselves. It's a lengthy process, requiring a deep layer of soil to be removed to get to the fossils. But after several days, the team's work starts to show results.
Look at that. That's quite a big deal. Just there, at the edge. Oh, wow. That's one. So here, at the edge of the plate, you can see very fine little filaments, and these are feathers, dinosaur feathers. You can see that the filaments converge towards the base, so these are composite feathers. It's a primitive kind of down that we find on some primitive dinosaurs.
Compared to the impressive Chinese discoveries, these fossils may seem a little underwhelming. But the paleontologists are thrilled to discover a completely new animal species. During the Jurassic period, the Chinese peninsula was covered in a vast forest of conifers, while Siberia was much more hostile. The arid climate had huge seasonal variations in temperature and intense volcanic activity, one of the keys to conserving precious fossils. Only fragments of skeletons are found at Kulinda. To begin with, the Russians thought that the feathers came from fossilized birds, the scales from crocodiles, and the bones from a small predatory dinosaur. But Pascal was not convinced by this hypothesis. In 2014, he reanalyzed all the fossils and suggested an entirely different explanation.
It's a bit like going into a cemetery and gathering up loose bones. You'll have small tibias, large tibias, little femurs, and big femurs. But they all have the same morphology, so we can tell they all come from the same type of dinosaur that we called Coelurosauropithecus. Because of the large number of disconnected bones that we found at Kulinda, we now know that Coelurosauropithecus was a small, herbivore dinosaur that was fast, slender, and agile.
This is the first ever feathered herbivore dinosaur to be discovered, a separate branch of the dinosaur family tree from the carnivorous theropods. Coelurosauropithecus lived in herds. Just like wildebeest migrations in Africa, large predators, such as Sinraptor, must have closely followed the movements of these dinosaurs.
This is a real revolution. What it means is that all dinosaurs could potentially have had feathers.
Feathers would have appeared on an ancestor that was common to both groups. It could be as old as dinosaurs themselves, first seen in the Triassic period 220 million years ago. The misfortunes of this group of herbivores have led paleontologists to the origins of feathers. Thanks to Coelurosauropithecus, we now know that the first feathered dinosaur, the common ancestor of the carnivores and the herbivores, remains to be found in fossil beds going back to before the Jurassic period. But who knows what other secrets could be found in Siberia? And what clues could be hidden in other parts of the world to document the early history of the bird dynasty? study the mammals that lived during the age of the dinosaurs, paleontologists were dependent for a long time on tiny fragments of fossils. They believed that mammals at that time were no larger than a mouse, and that they had only flourished after the extinction of dinosaurs. But the discovery in China of amazingly well-preserved fossils at the beginning of the 21st century revealed that mammals were bigger and more varied than previously thought. Detailed analysis of their physical features allows us to understand how they were able to coexist with their carnivorous neighbors and even outlive them. The fossils of these amazing mammals were found in the volcanic region of Liaoning, northeast of Beijing. Reponomymus was the size of a wolf and was able to devour young feathered dinosaurs. They must have been victim to large predators, like these Eutyrannus, but they are much bigger than all previously known mammals. These Reponomymus lived 130 million years ago in a highly active volcanic area. Preserved in fine volcanic ash, their skeletons have survived the ages. Radically changing paleontologists' understanding of the first mammals.
These fossil mammals are certainly related to our own evolutionary history in the sense that we ourselves are mammals.
Mammals, whose name comes from mammary gland, are the only animals to suckle their young. Their characteristics include fur-covered bodies, ears that are separate from their jaws, and a great variety of teeth, all of which, according to the latest fossil discoveries, were already present at the time of the dinosaurs.
And what we see is that they go from having teeth with a few cusps on them to having teeth that have many different cusps or tools, such that they were able to survive the mass extinction that killed off dinosaurs.
The fossils discovered at the beginning of the 21st century show that the first modern mammals appeared 125 million years ago. But genetic analysis indicates that they may go back even further. Until the discovery of new evidence, controversy rages between geneticists and paleontologists. It all began 250 million years ago, at the beginning of the Triassic period, during a time when the world was extremely hot. The ancestors of the mammals were mammalian reptiles, like these Thrinaxodon, a relative of the reptile family. Thrinaxodon is considered to be a transitional species in the evolution towards mammals. Like reptiles, its legs are not under its body, but on the sides, and it has no external ears. But like mammals, it has several different kinds of teeth, and its body is covered with fur. To escape the heat, it dug burrows along the banks of rivers, which is where it was fossilized. New X-ray technology at the synchrotron radiation facility in France enables scientists to analyze this South African burrow discovered in the 19th century. Using this innovation, Vincent Fernandez is able to study the contents of the rock without destroying it.
We discovered this burrow on a site where a road was under construction, and amidst all the burrows we discovered in this small quarry, this one had small bones in it, which gave us the idea of extracting it completely and studying it here at the synchrotron in Grenoble.
This tunnel was buried 250 million years ago, at a pivotal moment in the Triassic period, when 70% of the planet's terrestrial species disappeared. This block of stone may be able to tell us more about what happened to the survivors of this dramatic extinction.
The best way to find out which animal used which burrow is to find the animal directly inside the burrow, and to find this animal, rather than clearing the rock by hand, we will use X-rays to study the animal inside the fossilized burrow.
100 billion times more powerful than hospital X-rays, the synchrotron is able to distinguish the difference in density between fossilized bones and the rock itself. This high-resolution technology revealed the presence of a Thrinaxodon, a long-lost mammal ancestor, plus an unexpected bonus: an amphibian named Brumistega lying by its side.
This is a very big surprise because, first of all, we did not expect that, but mostly it's very rare because animals don't usually share the same burrow, especially with animals that are the same size and have the same diet.
Just as some mammals hibernate to protect themselves from the cold, this Thrinaxodon burrows underground and estivates to avoid the heat. In this dormant state, it may not have been aware of the Brumistega taking refuge in its shelter. The amphibian could also have been hiding from the hostile climate, and its fossil shows that it was injured.
We discovered that the Brumistega was wounded. It had a series of 7 broken ribs that were healing. We know that because it has small bone growths around the fractures, so we see the healing process. We know it was probably injured for several weeks.
This discovery revealed that mammals' ancestors had developed the ability to enter into a state of torpor. One wounded, the other asleep. Both animals would have been taken by surprise by the rising waters.
The lineage to which Thrinaxodon belonged was capable of surviving because it could dig underground tunnels and withstand droughts thanks to its specific metabolism. The fact that this lineage survived allowed for the emergence of mammals several million years later.
Vincent and his South African colleagues are now searching for new burrows to scan, hoping to solve other mysteries.
We are also looking for an egg or a pregnant female that will finally tell us which mode of reproduction our ancestors had.
It's a difficult task because mammal fossils from the Triassic period are very rare. Until the late 20th century, the only remains we had of the first mammals were their teeth, like these tiny specimens that are preserved at the National Museum of Natural History in Paris. Mammal specialist Emmanuel Guebron remembers his early years as a paleontologist.
When I started my career in the 80s and 90s, most of the remains we found were isolated teeth. We dreamt of finding not only jaws, but complete skulls.
These tiny fragments are obtained through painstaking work. Paleontologists must sieve several tons of sediment to uncover just a few of these mammalian teeth. The teeth are well preserved because tooth enamel is particularly resistant to time. It is the hardest part of the skeleton, the part that fossilizes best.
The interesting thing about these collections of isolated mammal teeth is their small size. You can have a collection of several hundred teeth, which will fit into a shoebox. So you can have the representation of a very diversified fauna, even the history of a whole geographical province, which boils down to a collection in the drawer of a cabinet with several hundred teeth.
That's exactly what the collection studied by Emmanuel Guerpron's team looks like. Started in 1976 in a fossil deposit near Nancy, in northeastern France, it now contains close to 1,000 teeth from the Upper Triassic period, 210 million years ago. This is the oldest collection of mammals in the world, with a dozen different species identified solely through the shape of their teeth. On these molars, the three cusps are exclusive to mammals. The molars are used to grind food, while canines keep food in place, and incisors cut. This complex dentition indicates that these animals are mammals, since other animal species have only one type of tooth.
The shape of teeth is like an identity card to show what group they belong to. It's an identity card to identify the animal, and it also reveals functional information. In other words, the animal's diet. Because sharp teeth, for instance, indicate an insectivorous diet. But if they have rather flattened teeth, that indicates a herbivorous diet.
Though they tell us more about how these dinosaur-age mammals ate, the fossils give no indication as to what they looked like. However, a tiny clue, discovered in France in 2008, reveals more about the skin of these extinct animals. This abandoned quarry is located near the town of Pangea, on the west coast of France. On this sand excavation site, two paleontologists from the University of Rennes take advantage of the exposed walls to come and collect fossils. This geological layer dates from the Cretaceous period, 100 million years ago. At the time, it was covered by a forest of conifers and ginkgo trees, whose remains have been uncovered by Romain Voulot and Didier Néraudot.
Look at this. This leaf has been in clay for the past 100 million years. Comes off, and if I blow on it, I can bend it, which shows that it's still flexible.
Apart from its change in color, the passage of millions of years doesn't seem to have altered this leaf significantly. The paleontologists are searching for another treasure in this petrified forest. Occasionally, bits of animals become trapped in the resin from conifer trees. When the resin fossilizes, it becomes amber.
So, here we are at the bottom of the quarry. Water has poured down and created an interesting little outcrop, because you can see the different layers. The layer is streaked because you have different alternating sediments. You will have two main types of deposits. you find sand deposits, white, ochre and red, and then another deposit from an accumulation of coal, which forms these small black veins. So here you can see sand alternating with clay beds that contain plant debris and small pieces of amber, which is what we're looking for in particular.
The sediment is then sieved in a nearby pond.
We've got quite a few small fragments here.
That's a good-sized piece. It's slightly translucent, part brown, part red.
Paleontology relies on meticulous work and a fair amount of luck. One major clue to the appearance of mammals was discovered thanks to an incredible stroke of good fortune. While looking for bacterial filaments, one of Romain Voulot's colleagues made an exceptional discovery. 2 hairs trapped in amber.
So we see the whole piece of amber, and in the middle, the longer of the 2 hairs, which is slightly bent. As you can see, it is very, very fine. We compared this 100-million-year-old fossil hair with the hair of current mammals, and we found that this one presents many similarities with what can be found in existing species, including scale morphology and scale layout. And their contours also show strong similarities to the hair of living animals. From a paleontological point of view, this is an outstanding discovery, since there are only 1 or 2 fossil mammal hairs in the world.
100 million years ago, warm-blooded mammals already had the same hair as today to protect them from the climate and allow them to survive the extinction that decimated large dinosaurs. In China, at the beginning of the 21st century, new clues to the physical appearance of mammals were unearthed. In a deposit dating from the Cretaceous period, 125 million years ago, fossils were discovered in an area that was once a peninsula with a subtropical climate. This world, dominated by huge dinosaurs like these 30-foot-high titanosaurs, was also home to mammals. Like this Eomaya scansauria, literally, ancient mother that can climb. Preyed upon by feathered dinosaurs like this Zhenwan long, Eomaya was the oldest known mammal ancestor when it was discovered in 2002. Located in the Liaoning region, northeast of Beijing, this deposit was once a volcanic area that has preserved our distant past for millions of years. Xie Luo, an American paleontologist of Chinese origin, is at the Siheitun Cliff, where many long-lost fossils have emerged.
This Yishan Formation is lake deposits and it trapped all variety of fossil vertebrates. Most famous of all are feathered dinosaurs, but very important for understanding our own human beings' early evolutionary history are these Cretaceous mammals.
125 million years ago, multiple volcanic eruptions created a series of sedimentary layers. Pockets of red ash flattened the mammals into the gray mud, like a printing press. Measuring 6 inches from nose to tail and weighing around an ounce, Eomaya would have been fair game for the feathered dinosaurs.
The fossil mammals are preserved very well because they lived nearby shallow water lake. The sediments accumulated fairly slow, and also there are occasional volcanic eruptions, so the hot volcanic ash helped to trap these fossil mammals in the sediments, and that is why they are preserved so well, therefore gave us this beautiful fossil to study.
At the Natural History Museum of Beijing, Xie Luo studies fossils of the Eomaya Scansauria group, placental mammals whose fetuses are sustained in the uterus by a placenta, just like humans. The whole body of the animal is beautifully preserved, a dream come true for any mammal specialist.
It is absolutely amazing that we have the entire fossils here. With the complete skeleton, we can start to flesh out a more interesting picture about these earliest mammals. These guys lived in Cretaceous. It has very gracile jaws, and we can recognize, even with naked eye, the limbs are quite slender, and we can tell by its very long fingers and the different nail structures that they are tree climbers. It shows that the placental ancestors are capable of exploring the arboreal or tree living niches than all these other contemporaries, and this gave us a big evolutionary advantage.
Eomaya left its young high up out of reach of dinosaurs that sometimes slept on the ground. These very first mammals would have to leave their shelter in order to drink. Their extraordinary mobility is revealed by this skeleton, particularly by the elongated trapezoid bones, which resemble those of tree-dwelling primates.
It is really by studying the ankle joint, we are able to recognize great many features to place this particular fossil on the line that eventually gave rise to modern placentals.
Its feeding habits were revealed thanks to its extremely well-preserved teeth.
You can tell that these mammals have a very sharp cusp in the front, and in the lower teeth, generally there were a series of very sharp triangles, and those are very effective for cutting the skeletons of insects and also slice off the flesh of worms.
After the discovery of Eomaya, more fossils were unearthed in China, changing the vision that paleontologists had of ancient mammals. Countless wonders are kept at the Institute of Vertebrate Paleontology in Beijing, Among them is a Reponomamus with a complete and unusually large skeleton. Yongqing Wang is the paleontologist in charge of studying this strange 30-inch creature, unearthed in 2004.
A lot of Mesozoic mammals that's about the size of mouse or rat. So this is quite big.
Another feature of this large mammal is its sharp, pointed teeth, embedded in a strong jaw.
Before we found this animal, we know the Mesozoic mammals, usually we thought they are insectivorous and small, living in the shadow of dinosaurs. You can see the teeth like sharp and pointed, so it's a carnivorous animal. Especially in his stomach area, there are some fragmentary bones of baby dinosaurs called Psittacosaurs. So we said, oh, okay, this guy ate dinosaurs.
The animal's stomach contents are revolutionary. They contain proof that some mammal ancestors actually fed on young dinosaurs, rather than living in their shadow. Paleontologists do not know exactly how they hunted. But they believe Reponomamus worked together in packs, like wolves. The Beijing collection has many surprises in store for scientists. Discovered in 2006, Volaticotherium has an unusual feature: a large fold of skin connecting its upper and lower limbs. Observed under a microscope, this dark stain reveals the presence of numerous hairs. Called a patagium, it's a fine membrane of skin covered in fur. Like a flying squirrel, the taut skin stretched between its limbs meant that Volaticotherium was able to glide from the trees. Before this discovery, scientists believed that bats were the first flying mammals to appear 50 million years ago. Volaticotherium, who was around at the same time as the dinosaurs, showed that flying mammals were around long before that. This nocturnal hunter waited for dusk to start searching for its prey.
It's really interesting. It's told us the ecological diversity of the Mesozoic mammals is much wider than we thought before. Usually we thought that animals living in the tree or walking on the ground, but these animals can glide in the air.
This flying animal confirms that mammals had adapted to different environments long before the extinction of dinosaurs. Despite the discovery of these fossils in China, one question still troubled the scientific community during the early 21st century. When did placental mammals first appear? Geneticists and paleontologists thrashed out their opposing views in scientific journals. In the German town of Oldenburg, a team of researchers hunts down the genes of modern mammals in order to construct their family tree.
We can estimate by seeing how similar a gene is in two different species of mammal, how closely related they are.
Olaf Beninde Emmons is the author of a 2007 study which analyzed the genes of 99% of animals living today. This mammoth task required 8 months of DNA sequencing to track the genetic mutations of 60 markers throughout the evolution of mammals.
The molecular data will give us a much more complete picture. We have DNA here for many more species than we have fossil data for. The fossils will give us point estimates throughout the tree. The DNA will fill in the gaps and give us all the divergence times for all the species of mammals and all the common ancestors that were.
This method, called the molecular clock, shows that placental mammals separated from marsupials 160 million years ago during the Jurassic period. Then diversified during the Cretaceous period to form the current main groups: rodents, carnivores, and primates. An unexpected result, since no fossil of these early mammals has ever been discovered.
This was interesting because there's a very big disconnect between molecular studies and fossil studies.
In Pittsburgh, on the other side of the Atlantic, another study offered very different results. It is the work of John Whipple, a paleontologist at the Carnegie Museum of Natural History. Its starting point was the discovery of a skull found in a 75-million-year-old deposit in Mongolia. Named Malestis gobiensis, it has been studied from every angle since it does not belong to any known species. 400 of its morphological features have been compared to those of 82 fossil or living mammals.
What we did is we looked at the individual morphological features of this animal across a broad array of other fossil forms and living mammals to try to figure out what it was related to. And our study supported the traditional view that there were no fossils living during the Cretaceous that were members of the placental group itself. There were only the ancestors of the placentals living.
Which of these two studies should we believe, fossil or genetic?
The molecular studies all tend to say that the crown group orders, rodents, primates, carnivores, bats, they all have their origins in the Cretaceous when the dinosaurs were still alive. The problem is there's absolutely no fossil evidence supporting this.
Many of these modern groups, according to the molecular clock analyses, actually they should be present in the Cretaceous record. We can't find them.
There's no doubt that there were placental mammals in the Cretaceous. What's debated is what kind of placental mammals they are. And it's a question of who's right at the moment.
To achieve the most complete mammal family tree, both types of data will need to be refined, defining the pace of genetic mutations on one hand, and seeking fossil beds on the other, since new fossils would confirm the geneticist's hypothesis. In the meantime, paleontologists are also trying to understand how these early mammals protected themselves from dinosaurs. The ability to nurse their young could have been a benefit.
If we want to understand how modern theories come from, we need to look at modern theorians' distant relatives.
Zangiotherium is a mammal that is even more ancient than placental mammals. This extremely well-preserved fossil was discovered in China in 1997.
We can be relatively sure it is a mammal because it had fur, and associated with fur would be a whole series of reproductive features. And so we know that it must have nursed its fetuses, but we don't know if the fetuses was born either in an egg or a live fetus.
Lactation offers an advantage when food is scarce, since the young continue to be fed thanks to their mother's body reserves. Lactation first appeared in the form of hundreds of milk-producing glands on the abdomen. Just like modern platypuses, the young would lick the thick milk from their mother's hair. Zangiotherium has another characteristic in common with monotremes, like the platypus, a spur on its hind leg.
This species definitely has another fossil that has preserved with a bony spur, and it's also consistent with the first observation directly from this particular specimen. In modern monotreme, this spur is definitely used for self-defense, but we do not know if it is truly poisonous or it's just a bony spur.
Snakes have fangs. Insects can sting. But this defense technique is rare among modern mammals. Located on the male's hind legs, this spur may have released a venom capable of paralyzing their foes. According to scientists, this weapon is not terribly efficient since it takes time for venom to have an effect. As they evolved, they tried other strategies, like running away. And to improve this tactic, what better than a superior sense of hearing? The evolution of ear bones was a key advantage for primitive mammals. In 2011, the discovery of this Leoconodon fossil shows at last how the jawbones of these reptiles migrated to form the middle ear of modern mammals 120 million years ago.
This specimen is the most complete mammal we have ever found in Western Liaoning. All the bones are preserved here. So it's a very beautiful specimen. Especially this specimen preserves some tiny bones of ear region. These ear ossicles usually is very difficult to be preserved in the fossils because it's very tiny. More important, it is a transitional stage of the mammalian middle ear evolution.
In ancient mammals, the lower jaw was linked to the skull by an elongated bone. In Leoconodon, this evolved to begin forming the ear bones. The hammer, anvil, and tympanic ring became completely detached in modern mammals to form the inner ear. Amazingly, every mammal embryo, including humans, reproduces this evolutionary phase in the womb, resulting in the formation of the inner ear. This precision tool allows us to analyze everything that happens around us, constantly.
Yes, it can hear the dangers earlier than the other kind of animals, so helps them to escape from the predator.
The mystery of the inner ear bones a link with our reptilian past, is cleared up thanks to this new fossil. Another mammal weapon, teeth, revealed their secrets at the University of Washington in Seattle. This is where Gregory Wilson uses state-of-the-art technology to analyze the teeth of multituberculates, mammal species that became extinct 34 million years ago.
We found some really exciting results, actually. What we found is that these multituberculates that were living alongside dinosaurs actually undergo an adaptive radiation 20 million years before dinosaurs go extinct. And what we see is that they go from having teeth with a few cusps on them such that they can eat insects and so on, to having teeth that have many different cusps or tools such that they can exploit a new resource in flowering plants. It's that ability to exploit that new resource that allows them to expand in terms of numbers of different species of multituberculates, as well as the range of body sizes that they have, such that they were able to survive the mass extinction that killed off dinosaurs.
His study shows that multituberculates evolved well before the extinction of dinosaurs. They moved from an insect-based diet to a diet based on fruit, or even angiosperms, flowering plants that appeared during the Cretaceous period. To reach this astonishing result, Gregory Wilson used fossils collected over 100 years in Montana's Hell Creek Formation. By studying this collection of tiny teeth under a microscope, he was able to familiarize himself with the many species of multituberculates.
This is the largest of multituberculates that lived, the size of maybe a beaver or a marmot. And it has many, many bumps all along the tooth row. And those bumps act as tools to crush and grind food. Another example sits inside this tiny vial. It's another multituberculate, but it also had teeth with many little bumps. So this was a smaller version of this animal that lived during the time of dinosaurs. This lineage we've known about for a very long time, but it's been difficult to really quantify or understand what the shape of those teeth mean. We've tried many different approaches, but none have really been able to give us the precision that we can now attain today.
This technological revolution came in the form of the CT scan, a medical imaging tool nowadays used by paleontologists. Specimens like this 67-million-year-old tooth are first scanned with X-rays on a microscopic scale. It is identifiable by its long incisor, but what intrigues researchers is the complexity of its molars. Once the data is collected, cartography software reconstructs an accurate map showing the shape of the teeth. Gregory Wilson has found that carnivores have a fairly simple tooth structure, with approximately 110 cusps per row of teeth, while multituberculate teeth are far more complex, with up to 348 cusps.
This particular specimen that I just pulled up has about 250 different complex little tools on the surface of its tooth row. And those little tools help break down plant material that needs to be processed very finely in order to be digested properly. So these guys have evolved towards eating plants.
It is this key function of grinding which promoted the explosion of herbivore and omnivore species, an ecological niche untapped by primitive mammals. Despite these multiple discoveries, at the end of the 20th century, the crucial question about the origins of the first real mammals remained. Once again, the Liaoning region provided the answer. In 2011, Chinese farmers found the fossil of a mammal called Jeremiah sinensis, meaning Jurassic mother from China. The paleontologist Shi Luo has come for the first time to visit this area, which stretches over several miles. It is not an easy task to identify fossil-bearing rocks under the fields of lush corn. But he is guided by a local specialist in feathered dinosaurs, whose oldest specimen, Anchiornis, was excavated on a site close to this one.
It's exciting fossil discovery because it gave us a new milestone as to when the placental lineage first started to appear on Earth. And all the modern placental mammals have a deep root into the Jurassic, and it's coming from right here. These rocks also are embedded with volcanic ashes, and these sites had been dated by geochronology to be 160 million, plus or minus a little bit. So we know for sure these rocks actually belong to the late Jurassic.
The Jeremiah sinensis fossil is the oldest specimen of a placental mammal and is a critical piece of the puzzle in the evolution of mammals. It was identified by its teeth, which included molars, canines, and incisors. As the genetic studies of living mammals showed, their origin is much older than existing fossils had suggested, since the discovery of Jeremiah means that placental mammals must have appeared at least 35 million years before Eomyascansauria. And even though paleontologists are still seeking fossils from the Cretaceous period, belonging to current groups like rodents or carnivores, this discovery brings the conflicting opinion of geneticists and paleontologists closer together.
Independent corroboration by fossils on one hand and by molecules on the other gave us the confidence that we are getting closer to the correct answer.
With Jeremiah, we know that 160 million years ago, mammals already had the characteristics that made them successful: fur, complex teeth, and acute hearing to escape predators and locate their prey.
The general adaptation, such as insectivory and such as the capability to move on the tree, gave this particular mammal some evolutionary advantage. It is really equipped well enough already in the late Jurassic for its descendant to thrive after the dinosaurs' extinction.
Certainly, the mammals' ancestors were very small at the time of dinosaurs, but much more varied and better equipped than was previously thought, with advantages that we find later in primates, our closest relatives. dragonflies the size of hawks, centipedes larger than humans, a strange menagerie of giant insects and amphibians reigned over the Earth 300 million years ago. Over time, these huge creatures shrunk in size or disappeared. The reasons for their progressive extinction remain controversial. $358 million years ago, the continents came together to form the supercontinent, Pangea. This was the beginning of the Carboniferous period. Oxygen levels in the air were much higher back then, 35% compared to today's 21%. For the first time on Earth, giant trees stored carbon dioxide and released oxygen in abundance. Human beings would not have survived in this high oxygen atmosphere. But for some swamp dwellers, it was ideal. Like Archaeopteryx, measuring up to 10 feet. This long-lost cousin of the centipedes was a herbivore. Or Meganora, with a wingspan up to 25 inches, this member of the dragonfly family is the largest known flying insect ever discovered, a tireless predator. It had no airborne competitors at the time, since birds and flying reptiles didn't exist yet. The high oxygen levels in the atmosphere give the characteristic sepia color to the sky during the Carboniferous period. Oxygen also makes the air extremely flammable. Such a hostile world is hard for us to imagine. Lightning storms could set aflame the immense forests and their inhabitants. During this period, not a day went by without huge forest fires, and yet giant insects thrived. Later, when fires became less frequent, these astonishing creatures simply disappeared. Scientists are trying to determine what caused their extinction.
There are several possible culprits. In fact, it's a bit like an Agatha Christie novel, when there's not one, but several murderers. It's our job to take the clues we have and reconstruct the investigations in order to come up with the most likely scenario.
While we've known about giant insects since the 19th century, paleontologists did not understand why they had disappeared. For a long time, a change in the composition of the atmosphere was the only explanation. But at the beginning of the 21st century, the discovery of fantastic fossil insects and their predators opened up new possibilities.
While that's a wonderful hypothesis, and assuredly something was preying upon these giant insects, we don't have great evidence for it.
Around the world, American, European, and Chinese scientists confront the old theories using new fossil discoveries unearthed by groundbreaking technology to try and explain why these giants became extinct. The earliest giant insect fossils were found in the French region of Allier in 1880. Under the surface of this pond were the remains of animals that had died 350 million years ago during the Carboniferous period, Meganeuras. Now extinct, these tireless predators are the largest flying insects that ever existed. This abandoned industrial site was an important coalfield in the 19th century, and as the coal was dug out, fossils were discovered close to the town of Commentry. The owner of the coal mine, Mr. Moni, gave his name to the specimen that is preserved at the Natural History Museum in Paris, Meganeura moni. André Nel, a paleontologist whose speciality is early insects, watches over this valuable piece.
Miners would look for fossils to make a little extra money. And one day, when they were opening slabs, they came across this animal. Unfortunately, when they were digging it out, they hit it 4 times with a pick and we lost its head. They were the super predators of the time, predators of other insects that were also very big.
These large-sized fossils are quite exceptional. While thousands of insects were found on the site of Commontree, only 5 Meganeuras were ever discovered.
Meganeura, like all other insects, had 4 wings, 2 on each side attached to the thorax in the center. In front you had a head with big eyes because it was a predator, so its eyes, just like modern dragonflies, were used to see its environment in 360 degrees, so possibly even behind the animal.
To better understand how this extinct animal once lived, we must step back 300 million years in time. This is what the French region of Allier would have looked like then. A giant swamp scattered with cypresses. Humidity at nearly 100% made the atmosphere dense and allowed Meganeura to easily carry its heavy exoskeleton into the air. It is part of a genus that is extinct today, but it looks much like modern dragonflies and is part of the same Odonatoptera superorder. With wings that functioned independently of each other, Meganeura was agile in flight, but unlike its contemporary cousins, it couldn't fold its wings. Faced with this efficient airborne predator, vegetarian insects such as Palaeontologists had to keep themselves out of sight. By comparing its anatomy to modern dragonflies, we can guess at Meganeura's main physical characteristics. 1, it could fly over 40 miles per hour. 2, it was a sight predator. Its head was independent from the rest of its exoskeleton, so it could keep it still while flying and focus on its prey. 3, it had a huge appetite. It could eat its own weight in food every 30 minutes. To catch all this food, Meganeura had an array of attributes identified in fossils. But what might explain its giant size? Away from the public is the museum's library of species, where they keep the specimens that scientists study. Here we find Meganeuras and their prey, both reaching impressive sizes.
So here you have an example of a Meganeura, on which we see the base of its wings, the thorax, but what is most spectacular are the 4 legs equipped with strong spines that were used to stab prey. But the Meganeura's prey were also large-sized insects, like the Palaeontologists. You just have 1 wing from here to here, so you can imagine the whole thing. These were Meganeura's prey. They were big guys too. Big insects to escape big predators. So in this case, we have an arms race between predators and prey.
But this battle to be the biggest between Meganeura and its prey seems to have had its limits. Otherwise, paleontologists would certainly have found even bigger and more terrifying flying insect fossils. Most of Meganeura's day was spent looking for food, since its metabolism required a lot of energy. According to scientists, the huge size of insects during the Carboniferous period was possible because of the high levels of oxygen in the air. Insects don't have lungs, but instead use a unique system of tubes, trachea, and tracheoles to bring air directly to their organs, including their digestive system. The downside to this system is it lacks efficiency. Air travels through the tissues in the form of gas. The bigger an insect is, the more oxygen it needs.
It is very strange that these animals reach these sizes, because nowadays we do not have such big insects. And at the time of the dinosaurs, when we had large vertebrates, insects were much smaller. It turns out that in the Carboniferous period, for reasons linked to geochemistry, the oxygen rate in the atmosphere was higher than it is today, which encouraged the development of animals such as the large insects.
Meganeuras could not survive in today's atmosphere because not enough oxygen would reach their organs, including their brains, and they would faint. Since the beginning of the 20th century, scientists have proposed a link between the size of insects and the concentration of oxygen. But it wasn't until 2007 that an experiment finally proved it. In the Chicago suburbs, the Argonne National Laboratory houses the United States' most powerful synchrotron, a scanner that generates the brightest X-ray beams in the Northern Hemisphere. The distance around the particle accelerator is more than half a mile. So Jake Soka, the scientist in charge of the study, uses a trike to get around. Today, live insects are being put under the scanner.
We use the idea that you can take living insects and make inferences about insects that existed in the past. What we're trying to do in this study is to test an old hypothesis that the amount of oxygen in the atmosphere is what limits insect body size. So the idea with this hypothesis is that when you have more oxygen, your insects can get larger, and when you have less oxygen, insects will get smaller in response. But no one had really ever tested this hypothesis before. So we use synchrotron X-rays to look inside the animal to study the dimensions of their tracheal system.
This particle accelerator generates extremely intense and focused X-rays that pass through the insect's body.
Our purpose is to see the tracheal system in action, and some of the tracheal tubes are really small, and we want to see it in the living animal. So this is really the only technique where we can do all of those things.
For the first time, scientists are able to actually observe an insect breathing.
Would you turn the beam on?
Using this experiment, they discovered that crickets not only breathe passively, but also use their whole bodies to carry air to their organs.
And you can see that bubble in the gut moves forward to the head, and it moves backward. And every time it's doing that, it's synchronized with the compression of the tracheal system. The movements that you see here are not a passive effect. This is an active movement by the animal, and it's the ultimate cause of it are contraction of muscles.
Just as this cricket contracts its digestive system to send air to its organs, Meganeura would have contracted its abdomen to absorb the thick carboniferous air. The elastic exoskeleton would resume its shape once the muscles had completed their action. But beyond the discovery of this internal movement, what interests Jake Soka is the space occupied by the respiratory system within the insects' bodies. He has compared beetles of different sizes to study the link between their size and that of their respiratory system.
And what we found is that the tracheal tubes take up a larger fraction of the body as you go from smaller to large than you might expect. So what we think, based on the study, is that if you would make this even larger, so if we would scale this up farther and farther, eventually you reach a limit where you can't stuff more tracheal system inside the animal because you have to have other things like muscles and gut and nervous tissue, fat bodies, things like that that are all important for the physiology of the animal. You can't just have one big tracheal system.
The higher oxygen concentration of the Carboniferous period meant that insects required fewer respiratory tubes and could therefore grow to a larger size. But with the modification of the atmosphere, the giant insects had to reduce their size over millions of years of evolution. And not all of them survived these changes. 290 million years ago, during the Permian period, oxygen levels decreased from 35% to 23%, close to today's level. Pangea had already formed a supercontinent extending from one pole to the other. Surrounded by a single ocean, it was subject to extreme climatic conditions. The heart of the continent suffered drastic temperature changes, and deserts appeared. But at the equator, heavy rainfall allowed the great forests from the Carboniferous era to survive. During this period of major climate change, punctuated by the monsoons and the warming of the atmosphere, a living fungus appeared on the bark of trees. This tiny mushroom uses an enzyme to break down wood. Gradually, plant debris and dead trees decompose and no longer build up on the ground to form coal. The fungus stopped the accumulation of carbon on the ground, and instead it was recycled into the atmosphere. The proportion of oxygen in the air decreased gradually, with major consequences for the environment. This transitional period brought about the demise of Archaeopteryx, a distant relative of the centipedes. But why did the first giants of the Carboniferous period disappear? Could their lifestyle be responsible? In 1977, Archaeopteryx fossils were found in Autun, in the heart of the French countryside. The slag heaps surrounding this former mining town are hallmarks of its industrial past. In the local Natural History Museum, tribute is paid to the miners who discovered fossils while they were working. Among them, this impressive set of footprints, the most important ever found in France. They're examined by Sylvain Charbonnier, a specialist in arthropods, the family of invertebrates that includes insects and centipedes.
Here you can see a set of tracks. You have two trails that are parallel. This was made by an organism of quite a respectable size, an animal that must have measured around 3 feet long. It's just a fragment of the track that was probably much bigger.
Unfortunately, no adult-sized fossil has been discovered, but the paleontologists have found many smaller specimens in these coal deposits.
You can see here what this little creature looked like. These are juvenile specimens, which are tiny. Here's a complete specimen with its shell that is well preserved. So obviously this organism, as it grows, will produce larger trails when it moves.
Archaeopteryx was rather similar to modern centipedes. It could reach 10 feet in length, and it crawled on the ground or up trees in search of food. Life in the rainforests during the early Permian period was quite similar to that of the Carboniferous period. And there was enough oxygen in the atmosphere for Archaeopteryx to thrive and face unexpected predators such as Eriops. This amphibian locates Arthropleura using cells in its skin that detect vibrations on the tree trunk. But Arthropleura had a considerable advantage. The claws at the ends of its articulated legs allow it to grip the trunk, and its protective shell shields it against attackers. Arthropleura's disappearance may not have been caused by predators, but by decreasing food supplies. This creature was a herbivore. At the time, it would have had plenty to eat.
At that time, the vegetation was equatorial or tropical, so it was an extremely lush vegetation with a great variety of plants. These plants are in fact the origin of coal. Arthropleura lived in this forest environment. You also have on the other side trees and leaves that were found in Arthropleura's stomach contents. So it probably fed on these tree branches. Did they eat from trees lying on the ground or did they climb trees? These are hypotheses we will probably never know for sure.
These fossilized plants have been so well preserved that they still appear alive. But as they began to disappear, Arthropleura had to adapt.
This forest environment will tend to dry out at the end of the Carboniferous. The climate will change, the vegetation will disappear, and Arthropleura will lose its food source, which is probably one reason that explains its extinction.
Over a period of 10 million years, the atmosphere and the climate gradually changed, bringing about the demise of Arthropleura. The most recent fossils we have date from about 280 million years ago. Evolution could have retained smaller and more energy-efficient insects. However, in 2009, scientists were surprised to find new Meganeura fossils in the south of France. These specimens, discovered on sites dating from the end of the Permian period, prove that the declining oxygen rate cannot be the sole explanation for the extinction of giant insects. What clues did these unexpected fossils reveal? These deposits are scarce. Scientists know of only about 15 of them in the world, and like here, they've not been all fully excavated. This beautiful landscape with its typical red rock is located less than an hour from the French Riviera. This is one of the sites excavated by André Nel.
Here we are, 250 million years into the red continental Permian. Red Permian because the rocks have become oxidized. The iron is oxidized and has become red. So we are dealing with an environment that is extremely rich in organisms that have left their impact, but few visible fossils up to now. In any case, in this deposit. But fortunately, fossils have been found in other deposits.
It's in a similar geological layer that insect fossils from the Permian period were discovered in 2009, close to the French city of Montpellier.
For a long time, we thought that these giant dragonflies had existed during the Carboniferous period and at the beginning of the Permian, but they no longer existed towards the middle and end of the Permian. But we were surprised to discover dragonflies that were as big as those from the Carboniferous.
Paleontologists were perplexed, since the level of oxygen had already decreased by that period. In theory, giant insects should have disappeared, but the specimens of different sizes conserved in André Nel's laboratory in Paris proved that they were still around.
There are tiny wings with the Meganuridae like this one here. This is the size of a modern dragonfly's wing. We have much bigger species. Here is the rear wing of another Meganuridae, another species. This one too was a giant. We have bigger ones, but only fragments. This here is a piece of Meganuridae's wing. The size is comparable to that of the Meganuridae of the Coniferous. We estimate that its wingspan is around 23 inches. We see that with these animals there is great diversity. It's during this time that they become the most diversified. We have small ones, medium ones, big ones, and very big ones. This means they had not really become extinct at this period. This does not sit well with the scenario of extinction due to the decrease in the level of oxygen.
These recently discovered species of Meganeurus found in France have also turned up in the United States. Evidence of their existence is accumulating. Here is what the Earth looked like during the middle of the Permian period, a hot and humid world covered with tropical forests. With an oxygen rate just slightly higher than today, one animal species survived against all odds, Meganeurus, represented by this Meganeuropsis. This specimen, discovered in Texas, is as large as its French cousins. But how can an insect measuring nearly 2 feet survive breathing air that was much poorer in oxygen than in the past? Did it have an advantage that Archaeopteryx did not? The Meganeuropsis fossil was discovered in 1937 next to Kansas City in the USA. Professor Michael Engels is a paleoentomologist who has worked at the University of Kansas for the past 20 years. Author of the definitive work on the evolution of the insects, he is also the head of this collection, containing 4.7 million specimens, most of them contemporary insects.
These are some of the large insects that occur today, large moths, stick insects, beetles, dragonflies, and damselflies. And while they're pretty impressive in their size, none of them can compare to the giant insects of the past.
According to Engels, one asset which might have enabled Meganeurus to survive during the Permian period, despite the lower oxygen levels, is the movement of their wings.
You would have an easier chance getting a large flying insect than you would a large insect that doesn't fly. Wings are vital not only for the movement of the organism, but as the muscles contract to move the wings up and down, they actually press up against the air sacs and move air through the body. Flight actually confers an advantage to the giant insects in the fact that the actual movement of the flight muscles helps to support the metabolically active tissue within them by getting oxygen into an area where a wingless insect or other arthropod would not be able to.
This full-body ventilation could be the secret to Meganeuropsis' survival. The movement of its wings quickly brings air to the trachea, which then supplies the organs with oxygen. While the ground-dwelling giants of the Carboniferous period disappeared, this advantage would have allowed Meganeurus to continue ruling the skies during the Permian period, remaining at the top of the food chain in the swamps. This Diplocaulus, a now extinct amphibian, has no chance of going unnoticed, betrayed by its need for air. Meganeuropsis sees it as soon as it leaves the water surface, thanks to eyes that are extremely sensitive to movement, shapes, and colors. Meganeurus were the super predators of the time, and their wings enabled them to survive despite falling levels of oxygen. So what caused their extinction? No Meganeurid fossils have been discovered from after the Permian period. Today, scientists still don't know exactly when they disappeared, but other large-sized dragonflies survived the next 130 million years. To explain the extinction of these giants, scientists are now contemplating the emergence of new predators. While insects were the only flying creatures during the first part of their history, other animals took to the skies during the later Permian period, between 300 and 250 million years ago, of what was to become, eventually, Europe. Jean-Sébastien Steyer, paleontologist at the Natural History Museum in Paris, is the leading French specialist in early vertebrates. He has come to the legendary Paleontology Gallery to collect a very important specimen for the study of insect predators. Though smaller in size than many other fossils, this was the first of its species to possess a major advantage.
This is the fossil of a gliding reptile that is about 250 million years old and has the strange name of Coelurosauravus. This reptile actually developed gliding flight.
The ability to glide allows an animal to catch prey in the air, like the giant insects. The planet continued to heat up at the end of the Permian period. Swamps, an infinite source of fossils, now had aquatic plants characteristic of stagnant waters. Like the insects during the Carboniferous period, reptiles were just starting to try out life in the trees and flying. Amongst them, Coelurosauravus would become an outstanding insect hunter, thanks to its retractable wings.
It had a very unusual and interesting anatomy. Its fairly small head was a triangular shape. On its skull, we can see small, conical pointed teeth. They were probably used to crack the hard exoskeletons of insects. And of course, the main characteristic of this gliding reptile are its stick-shaped bones that start around the armpits and enable this animal to throw itself in the air and base jump. We can well imagine it climbing up this microscope, for instance, and then jumping. We can even imagine it climbing with its small claws and then unfolding its wings to glide. So we can picture the race between Coelurosauravus and the flying insects living at that time.
Only 16 inches long, this small reptile couldn't catch Meganeuras, but it could compete for the same prey, the Palaeodictyoptera. To catch its victim, it has to take the plunge. Coelurosauravus can't flap its wings. To catch flying insects, it relies on an element of surprise. And its ability to glide. There is no room for error. Coelurosauravus is merely a first step on the road to flight.
This gliding reptile has no doubt played a part, maybe not in the full extension of giant insects, but in any case, we have a super predator regularly attacking them, and we can therefore assume that this was one element in the decline of giant insects at the time.
If Coelurosauravus was not the only culprit, it was certainly the first to put pressure on giant insects before any others took to the skies. This animal guarding the entrance to the Karlsruhe Museum in Germany is part of the pterosaur family. These flying reptiles appeared 230 million years ago. Today, they are completely extinct, but scientists have discovered around 100 different species. Could they, too, have been a threat to giant insects? Professor Eberhard Frey, or Dino as he is usually known, is a world specialist in pterosaurs.
Pterosaurs are flying reptiles, and they are characterized by a flight membrane that extended from the tip of the little finger down to the ankle. The interesting point with these pterosaurs is that they have a size range which is simply unbelievable, from about 20 centimeters wingspan up to 14 meters wingspan, which is unique.
Yet according to scientists, very few of these pterosaurs were insect eaters. The only insectivores were part of the Archaeopteryx family, among the smallest pterosaurs.
We cannot imagine really that they hunted the big insects, but probably they chased the small ones which are not seen in the fossil record. The big insects, however, also chased small insects, so they probably conquered about the same prey. All the other pterosaurs from that time we know likely fed on something else and thus did not make any concurrence to the big insects, and probably this is one of the reasons why they persisted such a long time.
230 million years ago, during the Triassic period, pterosaurs spread around Europe, but also to what is now South America and Asia. For the first time in the history of life on Earth, a family of vertebrates learned to master not just gliding, but flapping flight. Like Archaeopteryx, discovered in Germany, its Asian cousin, Batrachognathus, is a flying reptile, nocturnal, insect-eating, and fast. With its flat skull and big eyes, Batrachognathus occupies the same ecological niche as modern-day owls. But the comparison with birds of prey stops there. Its enormous jaws are equipped with a dozen conical teeth. No flying insect can hide from Batrachognathus volans, literally, flying frog jaw. Can the calligramma, an insect with a 10-inch wingspan, take it on? An experiment carried out in Germany puts the theory to the test. Dino Frey works in collaboration with the Institute of Fluid Mechanics in Karlsruhe, Germany. This wind tunnel is usually used to refine the shape of airplanes and improve their aerodynamics. But today, the paleontologist is using it to test the pterosaurs' flying abilities. A resin and carbon fiber model of Archaeopteryx is placed in the wind tunnel.
We are at the beginning of our studies, but what we learned so far is that pterosaurs likely were extremely slow flyers. Yeah? So they could cope with wind speeds around 40 kilometers per hour or less. That probably these guys needed to flap their wings to stay in the air, and that they were not very good gliders. But flapping wings also means that they were, as active flyers, much more maneuverable. And this is again interesting when they started to chase insects on the wing.
When pterosaurs appeared, insects lost the monopoly on flapping flight. Batrachognathus was indeed capable of leaving the tree-lined shore to chase insects out in the open, which his predecessor, Coelurosauravus, the flying lizard, was unable to do. The pterosaurs seem to have had more of an impact on the giant insect's prey than on the giant insects themselves, contributing to their final decline, but not fully explaining their extinction. On the other side of the Atlantic, one American researcher suggested other culprits in a study published in August 2012. This paleontologist specializes in the extinction that occurred at the end of the Permian period, 250 million years ago. More at home in front of a computer than wielding a trowel in the field, Matthew Clapham is a database devotee. It took him a year and a half to collect the information needed to publish his survey on the decline of giant insects. He has undertaken a mammoth task, gathering the sizes of all fossil wings since the first scientific publications.
We compiled this very large database with nearly 10,000 insect species by simply getting published papers where paleontologists had found insect fossils and described them and given them a name.
Clapham discovered that during the first part of their history, insect size changed with the level of oxygen in the atmosphere. As oxygen declined, they diminished in size, and as it rose, their size increased.
So this pattern holds for the first 200 million years or so of insect history. But then beginning in the late part of the Jurassic period, around 150 million years ago, you can see insects are become smaller, even though atmospheric oxygen is going up at this time. And this coincides quite closely with the evolution of Archaeopteryx, the first bird.
The ancient ancestors of the birds first appeared during the Jurassic period, 160 million years ago. The oldest fossils come from China. At that time, forests of giant conifers offered a fantastic launch pad to conquer the sky. An ecological niche that was quickly seized by a new generation of creatures learning to fly. Small dinosaurs, like this Anchiornis, had feathers on their arms and legs and used them as wings. The claws on their wings enabled them to gain altitude and get good vantage points. Insects, like this Duracimbroflebia, had to hide in the trees to survive. As soon as it takes off, it becomes visible and is hunted down by Anchiornis. While only a few pterosaurs, like Anuognathus, ate insects, all bird ancestors did. Increasingly skilled at flying, they would become fierce insect predators.
In the Cretaceous period, when these first birds are evolving, there would have been increased predation pressure on these large insects in particular, as they were less maneuverable than the smaller insects. In addition to this increased predation, there was likely competition between birds and insects, especially these large predatory insects, for the same food sources. And so both of those factors likely led to a decrease in insect size.
This competition between birds and insects still happens today. Just like flying lizards and pterosaurs, birds would have had an influence on the size of insects. But why have giant insects completely disappeared, leaving only today's small insect population? A last clue could provide an answer. It came from a fossil-rich site close to where Anchiornis was found, in the Chinese region of Liaoning, northeast of Beijing. The numerous eruptions that shook the region 125 million years ago have helped preserve certain plants from the period in volcanic ash, including the ancestors of flowering plants. Discovered in 2002 by the paleobotanist Sun Gay, they would have had an unexpected impact on the extinction of the last large-sized dragonflies.
But here in China, in the West Liaoning, we found all this known angiosperm we call the Archaeopteryx.
This is Archaeopteryx, the first flower to appear on our planet. On this fossil, seen through a microscope, we can distinguish the male organs, the stamens that contain the pollen, and the pistil, the female organ. These characteristics allow Sun Gay to confirm that this fossil belongs to the angiosperms. a family of plants whose seeds are enclosed inside a fruit, unlike conifers. According to the paleobotanist, these plants were aquatic and grew on lake shores. But what does the appearance of the first flowering plants have to do with the extinction of large carnivorous insects? André Nel believes these two events are linked.
Many families of insects disappeared at that time, and others managed to adapt to angiosperms, which proliferated and began to diversify to produce more or less our modern forests. The impact was also very significant for dragonflies during that same period.
Could the decline of giant insects have something to do with the dragonfly's original shape? Because before they were able to fly, they were aquatic creatures. Their life began underwater. For the first few years, they existed as larvae. And just like their cousins, the mayflies, they fed on other aquatic insect larvae. When flowering plants, such as Archaeopteryx, appeared on the lake shores 125 million years ago, the larvae's life conditions changed. The plants took root in shallow waters, but then opened their flowers in the air. When they withered, their petals and leaves floated on the surface before sinking to the bottom. This material is digested by the microorganisms present in the water, but to do this, the organisms use the oxygen contained in the water, leaving little oxygen available for the dragonfly larvae.
These dragonflies may have disappeared at that time because their larvae could not adapt to this change in the aquatic ecosystem, and they were replaced by other dragonflies.
The emergence of flowering plants completely modified the lake's ecosystem and would have led to the extinction of the last large-sized insects which had gradually declined since the Carboniferous. The extinction of arthropods and giant insects over millions of years of evolution teaches us that it took many protagonists to cause the extinction of these species. The change in the composition of oxygen in the atmosphere, the emergence of new predators like flying lizards, some pterosaurs, and the bird ancestors, and finally, the birth of flowers. In the early 21st century, which are the largest insects that inhabit our planet? Today, insects can reach the size of a hand, but very few are bigger than this Chinese cricket. For we are at the dawn of a new phase of extinction, caused by humans, since the onset of the Industrial Revolution.
The large insects live mostly in tropical or intertropical climates. They are in danger since their habitat is at risk. If the forest in which the giant stick insect lives is in danger, the giant butterfly will of course disappear.
I certainly hope that we will continue to see them, but certainly with the rate of habitat destruction that's going on throughout the world, particularly in the tropical environments where many of these species occur, it is very likely that a lot of them will be lost, just like the giant insects.